Okay, so we're going to start our stuff on differentiation, differential calculus, and going to split this up over several videos for you to have a look at. So this is the first thing we're going to look at is differentiating by first principles. This is the first of two methods you will learn to find the exact rate of change at a specific instant, or said another way, it's the exact slope of a function. Remember that the slope is the rise over run, and if you were had a function that was a function plotted against time, then the slope would be the rate of change over time. We'll get more on that later. We'll just go into looking at finding the gradient of a curve, or the instantaneous rate of change, or the gradients. There's two different things, just things that are synonymous. Anyway, let's go on. Instantaneous rate of change of a function y equals f of x. Sorry, that's blocked out slightly there. My photo's in front of it. At a given point, p of x1, y1 is given by the gradient of the tangent of that function at p. Spoken about this in class. So here's our function, our curve y equals f of x. And here's our point, p x1, y1. And that line there is the tangent to the curve at this point here. Okay? So what they're basically saying is the gradient of this blue tangent gives the gradient of the curve, or the instantaneous rate of change of the curve at the point P. Okay, so there's the tangent. We would like to know if we can work out the slope of that, and we could do it by just working out rise over run, and we would get the slope at that point. But as I said before, to find out the slope at every point, therefore, would be really hard. We'd have to draw in an infinite number of tangents and do this calculation every time. It's too difficult. So calculus, differential calculus, or finding the derivative, gives us a much easier way of doing that. Okay, now it says here we're going to use limits to find a formula that will give us the derivative at any point x, f of x, on any general curve y equals f of x. This general process is known as differentiation. The specific method using limits that we're going to use here is known as differentiation by first principles. This is to distinguish it from the second, more efficient method, which is known as differentiation by rule, or simply differentiation. This second method is by far more common, and it's the subject of other PowerPoints, but it's the thing that mathematicians do on a day-by-day basis. Doing it by first principles is like with the training wheels. We forget that and move on to differentiation by rule. Okay. Yeah, it's just more of what it's saying here. Differentiation by first principle is far more laborious than differentiation by rule. In actual assessments, when a question asks you to merely differentiate, it actually means differentiate by rule. If you're required to differentiate by first principles, you'll be specifically told to do so. The words by first principles will actually appear in the question. Okay. Moving on, this section will introduce us to the method of finding the IROC, or the derivative, using limits. Here we go, differentiation by first principles. All these words are synonymous. Instantaneous rate of change of y equals f of x at this point is the same as the gradient of the tangent at that point, is the gradient of the curve at that point, the derivative of y equals f of x at that point, the differential of y equals f of x at that point, and the differential of, I don't know what's the difference there. They've done the same thing, it's just in italics. I don't know why they've done that. But anyway, all those terms mean the same thing. You need to get to understand that. Okay, just going on. We've done this one in class. Find the exact expression for the derivative or the gradient of the curve y equals f of x equals x squared at any point on it. Okay, so let p x f of x be the point at which we are trying to find the gradient. Let q, which is at x plus h, f of x plus h, be another point further up the curve, and they're going to draw that in for us there. There we go. So we're trying to find the gradient at this point down here at P. Okay, and P can be any point therefore, because it's just a general point x f of x. Okay, now just going to draw, it says join PQ with a secant, which is that line there. It's not a tangent, it's a secant, because it actually encloses a sector. And that's where it gets the name from. Okay, so join there. If you have a look there, well, it's marking out, just going, that distance there is h, because that point there is x, and this one here is x plus h. So that difference there is h. And this distance here is f of x plus h minus f of x. So we've got the rise and the run there, which is going to be handy. Okay, the gradient of this secant will be m equals y2 minus y1 over x2 minus x1. That's what we've seen before. Just your rise over your run. And in this case, it'll come to this formula, which will simplify down to, we know f of x equals x squared. We actually can see it's just on h there on the bottom, isn't it? Because the x's will cancel. But we know f of x equals x squared, because that's what we're doing in this case. It's a nice parabola there we've got. So f of x plus h equals x plus h squared. Okay, so m equals x plus h squared minus x squared on x plus h minus x. Keep going. There's our point there. So if we expand that, we get that, and we put it back in here, x squared plus 2xh plus h squared minus x squared on x plus h minus x. So that's the slope of our secant, and it comes to this. And if you can see, there's a common factor of h here, and that's going to cancel out. So m equals 2x plus h. Now we're going to use the limit. So the gradient of the secant joining these 2 points, P and Q, h units apart horizontally, is 2x plus h. Okay, this is going back. Now let the point Q slide down the curve to approach P. So now imagine that we're going to bring this down here all the way down, and all the time calculating m. So let's actually do this. Slides down the point, so imagine there. We could move Q to there, and then calculate m there. Imagine if it went down to there and calculate and draw that secant and that secant. And finally, you see, we keep drawing this secant. Then finally, when Q is virtually in the limit as Q goes to P, this secant actually becomes the tangent. So the slope of the secant therefore becomes the slope of the tangent. And the slope of the tangent at that point is what we call the derivative at that point. Okay, so the secant ultimately becomes the tangent. We say the tangent is the limiting position of the secant. So the gradient of the tangent is given by that. Okay, and in this case, it was for y equals f of x equals x squared. It came down to that, and then finally that. And now the limit, as h tends to 0, is 2x plus h, is like 2x plus 0, which is just 2x. And there it is. And that's what we got in class that time. So, for the parabola, y equals x squared, the gradient of the tangent at any point x f of x is given by 2x. Another way of saying is that the derivative of y equals x squared is 2x. Okay, thus at the point 2, 4, the gradient is 4. At the point 3, 9, the gradient is 2 times 3 is 6. At the gradient minus 4, 16, the gradient is 2 times minus 4. Okay, which equals minus 8, and etc. Okay, we'll stop it there and come back and do a bit more on first principles later.